Most people think regression is just about drawing a straight line through data. But in reality, regression is one of the most powerful tools in machine learning used for prediction, optimization, and decision making. In this video, we'll go through all types of regression using these slides. And in upcoming videos, we'll go deep into each type separately. Regression is a supervised learning technique, which means the model is trained using data where the correct output is already known. It models a relationship between independent variables, also called input features, dependent variable, also called the target. Regression helps us predict numerical values, forecast trends, estimate the impact of variables. Now, before jumping into types, let's understand why regression is so important. Regression allows us to make quantitative future predictions, which means we can estimate numerical outcomes such as revenue next month or expected demand. It helps turn raw data into actionable decisions. For example, regression can tell us how much revenue will increase if we increase our advertising budget by a certain percentage. Regression is important because it handles real-world continuous problems such as price, demand, and quantity, which cannot be solved using simple yes or no outputs. It forms the foundation of many machine learning models. Neural networks can be seen as generalized regression models, gradient boosting builds on regression trees, and generalized linear models extend regression concepts. Regression also enables optimization, allowing us to answer questions like what is the optimal price, what budget maximizes returns, and which input combination gives the best output. Another key advantage is that regression models, especially linear models, are explainable and interpretable, meaning we can clearly understand how each feature affects the output. Regression helps detect patterns and trends in data, making it useful for forecasting tasks such as sales prediction, demand forecasting, and economic modeling. Finally, regression acts as a bridge between statistics and machine learning, combining inference and hypothesis testing with prediction and generalization. Linear regression assumes a linear relationship between input variables and the output. In this equation, y is the output, x represents input features, beta values are coefficients, e is the error term. Simple linear regression is used when there is only one input feature and it models the relationship using a straight line. Multiple linear regression uses more than one input feature and is commonly used in real-world scenarios where multiple factors affect the outcome. Polynomial regression is used when the relationship is not linear but curved, and it introduces high-degree terms of the input variable while still keeping the model linear in terms of coefficients. Ridge regression uses L2 regularization, which means it adds the square of the coefficients as a penalty term to the loss function, helping reduce overfitting and handle multi-collinearity. Lasso regression uses L1 regularization, which adds the absolute value of the coefficients as a penalty, and one key advantage is that it can reduce some coefficients exactly to zero, effectively selecting important features. Elastic net combines both L1 and L2 regularization, making it useful when dealing with datasets that have highly correlated features. RSS stands for residual sum of squares. Residual means the difference between the actual value and the predicted value. Linear regression tries to minimize this error. Logistic regression is used for classification problems, even though its name contains the word regression. Binary logistic regression is used when there are only two possible outcomes such as yes or no and spam or non-spam. Multinomial logistic regression is used when there are more than two categories and there is no natural order among them. Ordinal logistic regression is used when the categories have a meaningful order such as low, medium, and high. Tree-based models do not assume any linear relationship between input and output. Decision tree regression works by splitting the data into smaller regions and making predictions based on the average value within each region. Random forest regression combines multiple decision trees and averages their predictions, which helps reduce overfitting and improves stability. Gradient boosting builds trees sequentially, where each new tree focuses on correcting the errors made by the previous ones. XGBoost, which stands for extreme gradient boosting, is an optimized and highly efficient version of gradient boosting. Light GBM or light gradient boosting machine is designed for faster training and better performance on large datasets. Cat boost or categorical boosting is specifically designed to handle categorical features effectively. Linear regression is best for simple problems where relationships are approximately linear. Logistic regression is used when we need to predict categories based on probabilities. Tree-based models are best for complex real-world datasets where relationships are non-linear and difficult to model using equations. In this video, we covered the complete overview of regression. In upcoming videos, we'll go deep into each type separately, including linear regression derivation, ridge versus lasso comparison, logistic regression intuition, and tree-based models like random forest and XGBoost. So make sure you subscribe and stay tuned for the detailed series.